We're going to start with a course on differential equation, and I'm going to give you the introduction of that one. We know the equation. For example, we're having y equal to 3x plus 5. We know this is a linear equation and it's going to represent a line. We have the quadratic equation. We put here x squared plus 5x plus 6 equal to 0. That's the quadratic expression, this equation. Equation, when we have equality, we say the equation. Similar to this one, we can say differential equation. So in these two words are coming, the word differential is coming, and we are having the word equation. So differentials tell us that there is some derivatives, rate of change. We can have dy by dt, or change in y with respect to x. It can be first derivatives. We can have the second derivatives, or derivative of any order. We can have this one. So this is the case when, for example, in these two, we are having y as a function of one variable, y is a function of x. And these derivatives, we say ordinary derivatives. So in case we are having here the function of two variables, for example, I have the function fxy equal to c. Now the derivative we are going to get here is not the derivative we say here, instead of f I take u. So I have here the derivative as partial derivatives, partial u by partial x, partial u by partial y, first order. Or we can have the second order derivative, partial 2u by partial x squared and partial 2u by partial y squared. These are my partial derivatives. So when I say I'm just discussing the equation, it means I'm having the equation here. For example, I can write dy by dx is equal to 3. So this is my equation. This equation is containing the derivative. A function contain any derivative, we say the differential equation. It can be an equation like this one. We can have here d2y by dx squared plus 4y is equal to 0. Is also a differential equation because it contains the derivative. Or I can have the equation partial 2u by partial x squared is equal to partial u by partial t. This is also an equation. Here we are having y as a function of one variable. Here we are having y as a function of one variable. But here we are having u, a function of two variables. So this is my function u, a function of x and t. So there we say the definition of a differential equation will be that any equation which contains the derivatives called the differential equation. Moreover, we can classify this one when it contains only ordinary derivatives, then we say ordinary differential equation. So I am having here these two equations as ordinary. We're having here ordinary differential equations. So this is my ordinary differential equation, this is my ordinary differential equation. Here I can see that this equation contains the partial derivatives. So I will call this one as partial differential equations. So in this course, we are going to study only the ordinary differential equations. So this is my ODE ordinary differential equation. And partial differential equation we say is PDE, partial P is for partial, D for differential, and X for equation. In this course, we're saying we are discussing differential equation. Our differential equation mean, now if we say that we are discussing only the ordinary differential equation, we say it's differential equation. When you just take this one, this means we have taken a function of one variable, and so we ordinary differential equation. As I mentioned, definition of differential equation is a differential equation and an equation which contains unknown functions and its derivative. That we say that's a differential equation. So we can have the example here. So as we have dy by dx is 2x plus 3. Here the function is y is a function of x, function of one variable. When you have the solution, there's a function of x. Now here again, we can see it here is y is a function of x. So function of one variable. Here also, we have the y as a function of x, function of one variable. Here y is x is independent variable and y is dependent variable. Here u is a function of x and y, and here is u is a function of x and t. So we're having these equations respect to variables. Now we can see here in equation 1, 2, 3, and 4, we are having the variable y is the function of x, and the derivative, we're having ordinary derivative. So these equations, we say these are our ordinary differential equations. So the equations I will classify this as the ordinary differential equation, ODE. This also ordinary differential equation, ODE. This one is also the ordinary differential equation. We say it's OD and E ordinary differential equation, also ordinary differential equation. And here this one is a partial differential equation because it contains the partial derivative. Also this one is partial differential equation. It contains the partial derivative. This one classification with respect to the derivative. Now we look on the order of the derivative. The highest order derivative is 1. So we say first order. It's first order differential equation. Here the highest order is 2. We look on this one, this is 2. So it's second order. Second order differential equation. Now look on this one, order is 3. So it's third order. Third order ordinary differential equation. Here we can see here order is 2, is second order. Second order differential equation. And here we can say order of this one is 2, this one 2 is second order. Second order partial differential equation. Also here the order is 4, is fourth order partial differential equation. So this is respect to order. So order is the highest order term. Here order term is of order 2, here is of order 3, here is order 4. So then we classify according to the order of differential equation. One more thing which one see, we have done here with the respect to derivative, the classification we have done, and classification we have done respect to number 1, respect to the derivative, and then we have done the classification respect to the order of the derivative. Now this was number 1. We have done the classification. With respect to the variables. So one variable function of one variable ordinary differential equation. Second, we have done with the order of the derivative. Order. Number 3 is degree. So degree we take the power of the highest order term. So we can see here, when we take this one, the degree of this term is 1. So we say it's of degree 1. We say it's of degree 1. Also here we can say the degree of this term is 1. We say of degree 1. Degree of this equation is also 1. Look on this one. The highest order term is d3y by dx cube. And degree is 1. Here degree is 4. But we will not take this degree. We'll take the degree of the highest order term, that's 1. So we say of degree 1. This one is also of degree 1. So here is the degree. But here we look on this one. This have degree 4. The degree of this one is 3. So we say second order and third degree 3, third degree or degree 3 of degree 3. This is order 1, order 2, degree 1, degree 1, degree 1, degree 1. So the degree of this is, of the both equation is 1. This is also degree 1. If any one of the term is different from 1, higher, then we take that one. So we have the classification with respect to the variable, function of one variable, ordinary differential equation, function of two variables, partial differential equation. Order is the highest order term, degree is power of the higher order term. Degree is power of the highest order term. Number 4, we say is homogeneous or non-homogeneous. It's very easy. We say if it contains the dependent variable, other terms, then it is homogeneous. Sorry, when it contains the highest or the dependent variable in all the terms, that's known as homogeneous. And if any other term is not there, that's non-homogeneous. You can see it here. Dependent variable is y is not present here, y is not present here. This is non-homogeneous. We say this one is non-homogeneous. So if we look on this equation, we can see it here. Y is present here, y is present here, y is present here. We say it's homogeneous. We say it's homogeneous. So I just put here also OG. If I look on this term, this equation, y is present here, y is present here, y is not present here. This is non-homogeneous. It's non-homogeneous. Look on this one, y is present here, y is present here, I put here y is present here, we say it is homogeneous. This is homogeneous differential equation. Here, look on this one, u is the dependent variable, is present in both of them, is homogeneous. U is a dependent variable present in both of them, this one is homogeneous. So we have in the classification respect to the homogeneous equation, very interesting, y equal to 0 is a solution. This is another way of looking at that y is present everywhere. So look here, when put y equal to 0 is a solution. When put here y equal to 0 is the solution. But here y equal to 0 is not the solution. Also here, when you say u equal to 0 is the solution, u equal to 0 is the solution, it's homogeneous. Here it is not the solution, here it is not the solution, and these are non-homogeneous differential equations. So we have the classification respect to variable, order, degree, and homogeneous. One more classification that we want to make is number 5. That's about the linearity. Linear or nonlinear. This depends degree of the dependent variable. If degree of dependent variable is 1, is linear. If different from 1, it's non-linear. Now we look at this one, and we can just see it here. Here degree of this y 1, this degree of y is 1, is linear. Here we can see degree of y is 1, degree of y is not 1 because you have power 4. We say this is non-linear. So we can see here, this equation in this term, the degree is 3, interest degree is 4. So we say here, this is nonlinear, this is nonlinear. So this is homogeneous, but this is a nonlinear differential equation. So as I mentioned here, the power y is 1, so it's linear. Here the power of the degree of y is 1 is also linear. Here we have seen this is degree is changed, this becomes nonlinear. This is also 3 and 4 is nonlinear. And these are also linear because degree of u is 1, degree of u is 1. We say this also a linear differential, partial differential equation, also a linear differential equation. So we're having the classification respect to variable, respect to the order, degree, homogeneous, and linear and nonlinear. We look on this example, I want to say these equations are nonlinear. But why they are nonlinear, that we want to see it here. We can see here, the coefficient of dy by dx is y. And we say y is repeating. So due to this term, this is nonlinear. Because y is repeating here. Now we say this is also nonlinear because when you see sine of y, we have sine of y, we can write in the series, and you can see the degree is more than 1. It's y cubed, then y5, then y7. So due to sine term, this becomes nonlinear due to sine y. And it's nonlinear due to the term that here the coefficient of dy by dx is depending upon y. If any of the coefficient is depending on y, then that equation will become nonlinear. So we can just change it. We write here y, this becomes nonlinear. Now here we can see in the first term, in this term, we can see it here. Now here this is nonlinear because we have the coefficient of d2y by dx square. Due to this coefficient, which is y, so this becomes nonlinear. So we can say here the degree of y is 2, also degree of y is 2 here, and here degree of y is increasing more than 1. If the degree of y is different from 1, then the equation becomes nonlinear. That's very simple to say it. Moreover, we just see it here. These were ordinary differential equations, all of them. This equation is, we can see it's homogeneous or non-homogeneous. We can see here, this is not containing y. It's x only. So this is non-homogeneous. Here, there is y in both the terms, is homogeneous. Here again, due to this x square, this is non-homogeneous. If I change it, for example, to 0, or we write here, then instead 0, or we write here, as for example, I say it is 2y. So this becomes homogeneous because these terms contain, all the terms contain y, and y equal to 0, as I told you, is solution of the differential equation. And y equal to 0 solutions mean homogeneous. So we can see it. Here we can see the degree of the differential equation. Here degree is 1, here degree is 1, here degree is 1. Order of the differential equation, order is the order of the derivative. So we can look on this order. This order is 2. Here the order of this one is 1. Here the order is 2. So we can classify our differential equation in different way. As we can see it, it is ordinary or partial, number 1. Number 2, we see the order of the differential equation, order of the highest order term in the differential equation. Then look at the degree. For degree, we look on the power of the highest order term, and that gives me the degree of the differential equation. Homogeneous is y equal to 0 is the solution of the differential equation is homogeneous. Then we have seen is linear or non-linear. We say y, the dependent variable, must have order 1 or degree 1, you can say. It's not having power, it's not repeating. The coefficient must not be a function of y, a function of the dependent variable. Then we say that the equation is nonlinear. And if it is only the degree of this one is 1 of y in each of the term, we say the equation is a linear differential equation. So we see how we can write the differential equation of different order. We have different way of. One is we are having the derivative. This dy by dx is the derivative. If I am having dx dy, that's the differentials. This is my derivative of y, and these are my differentials. So we can write the equation in the form of derivative and in form of the differential. Here we are writing the equation in form of the derivatives. So I can have here dy by dx written before. So these are all my derivatives. Now I can write here the equation like this one. I can write here, I have the equation dy by dx is equal to 3x plus 5. I multiply by dx, I get here dy is equal to 3x plus 5 multiplied by dx. Now this equation, this one is not the derivative form. We call this one as derivative form. Derivative form. And this differential equation, we say it is differential form. So these are the most important form we are having writing differential equation. This equation we can write in a very general form. We say we having a 1x dy by dx plus a 0x y is equal to any function of x, non-homogeneous equation. So it's my general form, and we say it's a linear first order. We call this one first order linear differential equation. And obviously it's homogeneous, non-homogeneous, because this term does not contain y, but we are having this standard. So I have three forms: derivative form, Number 2 is differential form. Number 3 is a first order linear differential equation form. As we have written here, the first order linear differential equation, this is my first order linear differential form. So I can write here this form, mxy in a general way into dx plus nxy into dy equal to 0. This is my general form, this is differential form. This is my differential form. In general, we write like this one. This is my number 1. You can say this is my number 2. Number 3 is, we know what we are having here. We are having the function of x, y, and dy by dx equal to 0. You can see it here. We are having x, we have y, and we are having dy by dx. We are having here x. So in general, we can write is a function of x, y, to any equation which is first order differential equation. We can write in this form, this general form. Or we can write also this one as dy by dx. We can rewrite our equation as a function of xy. This is also my general form of my differential equation. So these are my form that how I can write my differential equation. I can write it as first order linear differential equation because the coefficient are function of x only. If any one of these coefficient is function of y, they become nonlinear. So we say it's first order linear differential equation. Now we write instead of derivative differential dx and dy. So we say this is my differential equation in differential form. In general, we have seen that we have this is the functional relationship between y, dy by dx, and x. So we say the functional relationship between x, y, and dy by dx is my general form. Or we rewrite this one that dy by dx is a function. We can write our equation in this form. For example, I can just take this one to other side, divide by a1. So dy by dx become function of x and y. So these are my general form. In this form, we can write our differential equation. I write the general form of the second order differential equation. I know you know that I have the second order differential equation d2y by dx square in general form. I put a coefficient here, a2 of x. Is any functional relationship of a constant. Now we're having here a1 of x into dy by dx. We get here a0 of x, y equal to f of x is non-homogeneous. I can write this, for example, I can write here x d2y by dx square plus 3 dy by dx plus x square y is equal to sine x. So this is an example for this one. If it's a non-homogeneous. If I write here x square d2y by dx square plus 3x dy by dx plus 4y equal to 0, this second order differential equation in homogeneous form. If I want to write a general relationship, as I wrote before, this is a function relationship between x, y, dy by dx and d2y by dx square equal to 0. This is my function relationship. So this is my number 1, this is my number 2, and number 3 is I can write d2y by dx square is a function of x, y, and dy by dx. In a similar way, we can generalize this is my second order differential equation. As I said, is homogeneous form or non-homogeneous form, linear or non-linear. But here we're writing the linear differential equations. So we can have definition like this. Similarly, we can define the third order, fourth order, nth order differential equation.